So this time we're going to look at the specimen paper for the CCEA A-Level Chemistry A2 Unit 2. You might also know that as the Chemistry Unit 5, it's the same thing. This paper would be 2 hours long, and usually paper 2 in A2 has sort of 15 or 16 questions. This one actually has 17. So let's take a look at the multiple choice to begin with. So select the correct response in each case and mark its code letter by connecting the dots as illustrated on the answer sheet. Not sure you have to do that anymore, so ignore that. If you get a past paper like that, you just mark them now on the actual paper themselves. Each multiple choice question is worth 1 mark. Some of the legacy ones, you'll see they're worth 2 marks, so they tend to have a bit more work in them than these ones. So, number 1, which organic compound gives rise to the largest number of peaks in an NMR spectrum? So if we have a look at these different compounds, this one here, you might think, well, there's 1, 2, 3, 4 different lots of hydrogens, but actually, when we look at them, these ones on the left of the carbon with the oxygen attached to it are equivalent to the ones on the right, so we've really only 2 different groups of hydrogens here. In the next one, we've got 2 groups, there and there. In the third one, 2 groups. And if we look at the fourth one, there's a CH3, there's a CH2, and then there's this CH3 in a different environment. So that is going to give rise to the largest number of peaks. So your answer is D. Next, which is correct for a lithium-ion battery. So you can see I've actually circled the first one here because it is actually A is correct. The lithium ions move from the negative electrode to the positive electrode during discharge. You can see then that the other answers are clearly not true. The lithium ions move from positive electrode to negative electrode during discharge is incorrect. The battery can be used safely at high temperature is also incorrect, and the electrolyte is not, what it says, is an aqueous solution of a lithium salt when it isn't. Number 3, which statement describes the primary structure of a protein? Is it A, the folding of an alpha helix, B, the folding of a beta-pleated sheet, C, the sequence of amino acids, or D, the coiling of the chain? So it's the primary structure, which is the very first level of complexity, which is the sequence of amino acids in that protein. Number 4, which one of the following describes the charge and coordination number of nickel in the NiEDTA 2- complex? So we've got a choice here, and I can't actually see D. I don't know what's happened to it. It's disappeared, but it doesn't matter because it's not actually relevant. It's not correct. So for this complex, the coordination number, because it's EDTA, is always going to be 6, and that means that it has to be C, plus 2 for the charge. So EDTA, of course, has a charge of -4, and that's given us +2 altogether. Right, which one of the following is not present in a coloured compound? Or the following ions. So we've got here copper, iron, nickel. We know they're all transition metals. They're all going to be coloured. And zinc is the weird one because although it's in the transition block, it doesn't behave like a transition metal. Okay, so the answer is D. Standard electrode potentials for a series of redox equations are listed below. You can see here, we've got, as usual, the most negative at the top and the most positive at the bottom. Which element will reduce iron 3 to iron 2, but not to iron? So iron 3 to iron 2 is here. And of course, we want that to be going in this direction. Okay. And we want something then which will do that, but not then iron 2 to iron, which would also have to be going in the same direction. So looking at our choices here, if we look at iodine, it's here. Iodine is on the left, so to get that, it would be going the wrong way, so that isn't going to work. Manganese is right at the top, so manganese would go to the left. That would, it would cause that reaction to iron 2, but it would also reduce it, or cause the iron to go to iron. So not manganese because it says not iron. Nickel then in here. So if we went from nickel, that would reduce the iron 3 to iron 2, but not to just iron, which is at the top. And then silver, as you can see, is right at the bottom there, so it's not going to do anything. So the answer is C, with the nickel. Number 7, which one of the following pairs of monomers will not combine to form a polymer? So it's worth just looking at the monomers and seeing what they are. So here we have an acid and an amine, so that's going to give a polyamide. Here we've got 2 amines. Not going to give anything, is it? So that's the answer there. But just for completion, let's look at the other 2. We've got CH2, CH2, and CH2, CH2. That's 2 ethenes, so that's going to be an addition polymer of polyethene. And here then we have an acid and an alcohol, so that would give a polyester. So yeah, the answer is B. Then the complex MCl2NH3 4 times plus. What is the oxidation number of M? So looking at this, each chloride is going to be -1. There's no charge on those 4 ammonia. So -2 in total for the chlorines, and then that means the metal has to be +3 to give us our positive charge overall. Number 9, iodoethane may be converted to propylamine by reaction with, well, iodoethane to propylamine, you're going up 1, so it has to be potassium cyanide. And then if you were to react with ammonia, that's nonsense. So it's D, potassium cyanide, followed by lithium to add the hydrogens so that we get the amine. And then number 10, in a solution at pH 1, glycine exists as you've got a choice of anions, cations, dipolar ions, or neutral molecules. So think about in pH 1 solution, you've got lots and lots of hydrogen ions. So they're going to bind to the CO minus, and that's, then we still have the H plus on the other part of the Zweitter ion. So it's going to be cation ions there. So 10B cation ions. Okay. Number 11. The USA space program supported research to develop fuel cells. The shuttle missions used a fuel cell based on the reaction of hydrogen and oxygen in an alkaline medium to form water. Write the equations to represent the electrode reactions in an alkaline hydrogen fuel cell. So the key there is the alkaline hydrogen fuel cell. So the anode, 2H plus and 4OH minus, gives you 4 water and 4 electrons. And then at the cathode, O2 and H2O gives you 4 electrons and 4 OH minus. 1 mark for each of those. Then write an equation including state symbols for the overall reaction in the hydrogen-oxygen fuel cell. So when you add them both together, you end up with 2H2 and O2 gives us 2H2O. So that's overall equation. 2 marks for that, 1 for the left-hand side, 1 for the right-hand side. Or possibly actually 1 for the balanced equation and 1 for the state symbols. Yeah. So then 2 advantages of a hydrogen-oxygen fuel cell. So first one I would expect you to say is it's a source of renewable energy. You could say it doesn't produce pollution. And you could say it's silent. So any 2 of those would get you your 2 marks in that question. Number 12. Proteins are synthesized from 20 essential amino acids. Recent research has shown that some organisms also use another amino acid called selenocysteine, which is shown below. This is it here. Look. So it's got this selenium in it, which makes it a bit weird. So explain why selenocysteine, like other amino acids, would be expected to have a high melting point. Now, when you get something like this with a weird thing in it, like the selenium, just pretend it's not there when you're answering a question like this about the amino acids. So what it's asking really is, why do amino acids have high melting points? And the reason is because they're dipolar ions, and then that there's a strong attraction between the opposite charges. Okay. Then selenocysteine reacts with sodium carbonate solution. Write an equation for this reaction. So what you need to do is work out how to write the formula for this job here, the selenocysteine. And what I've done is I have my H2N and then a carbon with a CH3 and a CH2SEH. So that's the carbon, this methyl group, and then this with the selenium in it, and then the COOH, and then sodium carbonate is Na2CO3. And then with the same stem here, but with the Na on the end, and then any reaction of a carbonate with an acid will give you water and carbon dioxide as your other products. So 2 marks for that. Now just a word here, in the mark scheme, actually they have drawn, as far as I can see, the formula for the selenocysteine incorrectly. They have H2NCH, CH2SEH, COOH. So just be careful. Not, if something looks wrong in a mark scheme, check with your teacher or somebody like that. Just make sure that actually it is correct. So part C, some E. coli bacteria contain selenoproteins, which are enzymes. Draw the structure of the dimer formed between 2 selenocysteine molecules and circle the peptide link. So you see here again, this is the stem of the molecule here, and in this side I've got the CO from the acid, and here I have the NH from the amine, and we've got the peptide link which I have circled there. Okay. And then the dimer obviously is 2 molecules together. So explain the mechanism by which the enzyme works. Well, it's induced fit mechanism, and explaining that it lowers the activation energy. And then draw a graph labeling the axes to show how the enzyme activity is affected by altering the pH. So really what we're showing here is that there's an optimum pH. So I've got enzyme activity on the y-axis, and then pH on the x-axis, and I've drawn a bell-shaped curve. So in the mark scheme, it just said bell-shaped curve, 1 mark, and then the axis labelled is your other mark. So the next question is about electrode potential. So the determination of iron in its ores is an example of the application of manganate 7 titrations. Before titration with manganate 7 ions, any iron 3 must be reduced to iron 2. The reduction can be carried out with zinc amalgam, which is a mixture of zinc and mercury. So write an equation with 3 equations here. Zinc 2 and zinc, we have iron 2 and iron, we have iron 3 and iron 2, and the electrode potentials of all 3. So write the equation for the reaction between zinc and iron 2 ions. So I'm just taking the equations here and adding them together. So I've got Zn and 2Fe3 plus gives 2Fe2 plus and Zn2 plus. So 1 mark just for that. Then the use of zinc amalgam prevents the further reduction of iron 2 to iron. Use the electrode potentials above to explain why, in theory, zinc would also reduce iron 2 to iron. Well, if you look here, zinc, the reaction's going this way, and iron 2 to iron is going this way, so it should go ahead. And if you look at the difference in the values, it's 0.32 volts. So yeah, that's really what you need to say in your answer. The electrode potential is 0.32 volts, so the reaction should go ahead. Then manganate 7 is used to determine the concentration of iron in solution. The half equations are this, and you'd be very familiar with this by this stage. MnO4 minus and 8H plus, and 5 electrons gives you Mn2 plus and 4H2O. And then Fe2 plus gives you Fe3 plus and an electron. And really I would recommend learning this balanced equation off by heart, just so you can reproduce it straight onto the page. But most of you probably know it anyway. You need 5 lots of the bottom equation so that it balances with the 5 electrons in the top one. So it's MnO4 minus 5 Fe2 plus 8H plus gives you Mn2 plus 4 water and 5 of the iron 3 ions. Now when you get a question like this, there's usually going to be a calculation when they're talking about titrations. So a sample of steel with a mass of 1.6 grams was dissolved in an excess of sulfuric acid, and the solution was made up to 250 cubic centimetres with water. So several 25 cubic centimetre samples of this solution containing the iron 2 ions were titrated with 0.2 molar potassium manganate 7 solution. The average titer was 26 cubic centimetres. Calculate the percentage of iron in the sample of steel. So here we go. First thing you can do from the question is we know the number of moles. We can work out the number of moles of the potassium permanganate. So We've done that. Number of moles of the MnO4 minus is 26 by 10 to the minus 3. That's 26 cubic centimetres. You could do 26 divided by 1,000. It's the same thing. And then times 0.02, which is the concentration. And that gives 0.52 by 10 to the minus 3 moles. So we know there is a 1 to 5 ratio between the number of moles of the manganate 7 and the moles of iron. So we multiply that 0.52 by 10 to the minus 3 by 5, and that gives us 2.6 by 10 to the minus 3 moles. From the question, we know that that is in 25 cubic centimetres. So I've written there in 25 cubic centimetres. Now, in 250 cubic centimetres, we're just multiplying that by 10, so that's 2.6 by 10 to the minus 2 moles in the 250 cubic centimetres, which is 0.026 moles. So we want to find out the mass then of the iron, so it's 0.026 times 56, which is the atomic mass of iron, gives us 1.456 grams, and then the percentage of iron is just 1.456 divided by, in the question, it tells us 1.6 grams was the original amount. Okay, so 1.456 divided by 1.6 times 100, and that gives you 91%. 4 marks for that. And the marks are going to come from the number of moles of manganate 7 and the number of moles of iron, then the mass of the iron that you would have got, and then the percentage of the iron. So that's 4 marks in total. And of course we can't have a titration without a colour change question. So what's the colour change at the end point? Well, it goes from colourless to pink. Question 14. Amines may be prepared by the reduction of nitriles or by the reaction of ammonia with haloalkanes. 1-bromobutane reacts with ammonia by a similar mechanism to that of the alkaline hydrolysis of haloalkanes to form 1-aminobutane. Name the mechanism. Excuse me. It's nucleophilic substitution. And then write an equation for the reaction. It's not asking for a mechanism, just an equation. So C4H9Br plus NH3 gives you C4H9NH2 and HBr. So you see it's just a straightforward substitution there between the bromine and the NH2. So without using a flow scheme, suggest an explanation for the mechanism for the reaction. If you look at this bond, the carbon and bromine bond, it's polar because the carbon will be slightly positive and the electronegative bromine is going to draw the electrons towards it, so it's going to be slightly negative. Now, the ammonia NH3 has a lone pair on it, which is attracted to that delta positive carbon. So what you'll get is the bond forming between the carbon and the nitrogen and the bond breaking between the carbon and the bromine. So really 1 mark for each of those stages of the answer. The idea that the bond is polar, that the nitrogen's attracted to the positive carbon, and then that the bond forms with the nitrogen and breaks with the bromine. 1-aminobutane may also be prepared by the reduction of butane and nitrile. Name a suitable reducing agent. Lethal. And then using H in square brackets to represent the reducing agent, write an equation for the reduction of butane nitrile. So butane nitrile C3H7CN, and we're going to C3H7CH2NH2. So you see there's 4 hydrogens there, so we write plus 4H on the left hand side. Then we have phenylamine or aniline was discovered in 1826 by distilling the dye indigo. The name aniline is derived from anil, the Portuguese word for indigo. So reduction of nitrobenzene produces aniline. Write the equation for the reduction of nitrobenzene using H in square brackets to represent the reducing agent. So there we have our nitrobenzene C6H5NO2 and then the aniline C6H5NH2. We need to add 6 hydrogens to that then to make first of all the NH2, so with 2 adding to that nitrobenzene, and then to use up the oxygens we need 4 hydrogens to make 2 molecules of water, so it's 6 in total here. So aniline is basic and reacts with strong acids to form crystalline salts. State the basicity of aniline compared to ammonia and phenylethylamine. So we've got ammonia and then this aliphatic amine. So they're both more basic than the aniline, which is an aromatic amine. So the aniline itself is less basic than the others. Then write an equation for the reaction of aniline with hydrochloric acid. So aniline C6H5NH2, hydrochloric acid is HCl. We're getting then this C6H5NH3 plus HCl minus. Then explain why the phenylethylamine is a primary amine. Well, the phenylethyl group is attached to a nitrogen atom with 2 hydrogens attached to it. The easiest way to do that is just draw the thing out and have a look at it. So then when aniline is treated with nitrous acid at a low temperature, the benzene diazonium ion is formed. Draw the structure of the benzene diazonium ion, which is C6H5N2+, showing all the bonds between the nitrogen atoms and the location of the charge. Do not show the detailed structure of the benzene ring. That's nice. So we've got just benzene ring is C6H5. Then the 2 nitrogens joined with a triple bond here, and the charge is on the first one. Name the reagents used to generate the nitrous acid. We have sodium nitrite and dilute hydrochloric acid. You need both for that mark. And I should have said in this previous one, you're getting the mark there for having the thing correct with the bonds here in the between the nitrogens, and then the other mark would be for the charge in the correct place. Okay, next, if a solution of benzene diazonium ion is treated with aqueous sodium cyanide in the presence of a copper catalyst, cyanobenzene is formed. Name the reagents A to D in the following flow scheme. So, first of all, A, we've got this nitrile going to an acid, so that's going to be an acid HCl or H2SO4, or you can have sodium hydroxide. Then in B, we've got the nitrile going to an amine, so that's going to be lithyl. In C, we've got the amine going to an alcohol. So here we need either HNO2, NaNO2, either of those, and HCl. And finally in D, we've got the alcohol going to this chloride, so PCl5 or HCl. So it's worth knowing all of your organic interconnection or interconversions for this paper. Number 15, transition metal chemistry is characterised by catalytic activity, redox reactions, colour changes, and ligand replacement. Vanadium and chromium are typical transition metals. Explain in terms of electronic structure why vanadium and chromium are transition metals. They are transition metals because they have an incomplete D shell in their ions. Then an acidified solution of sodium vanadate 5 undergoes a series of reductions when it's stirred with zinc. Complete the table below, giving the colour of VO2 plus and V3 plus ions formed at different stages of the reduction. So the VO2 plus here is blue and the 3 plus is green. So you remember they go from yellow to blue to green to violet. Then chromium will also reduce ammonium vanadate. And we have here 2 equations. There's the chromium in the first one and then the vanadate in the second one. So write an equation for the reaction between chromium and the VO2 plus ions and calculate the EMF of the reaction. So it's going this way and this one is going this way. So it's just a matter of adding them together. So we have 3 VO2 plus and Cr and 6H plus gives us 3 VO2 plus, Cr3 plus and H2O. And then the EMF is just the difference between those two, which is 1.74 volts. So 2 marks for the equation and 1 for the correct value for the EMF. Now the colour of a transition metal complex depends on its coordination number and the ligands attached to the metal ion. This is illustrated in the following. We've got this hexaaquacopper complex going to this tetrachloro one. So state the colours of the two copper complexes. So the hexacycle one is blue, and then the chloro one is yellow, 1 mark for each. The shape of the hexacycle copper 2 is octahedral. Anything with a coordination number of 6 is going to be octahedral. Then name a suitable reagent which could be added to the equilibrium to shift it to the right. So either hydrochloric acid or sodium chloride, something which is going to give you these chloride ions, which will displace the water as a ligand. Then 1,2-diaminoethane is a bidentate ligand which can complexes with aqueous nickel 2 ions. Draw the structure of 1,2-diaminoethane. So it's just H2N, CH2, CH2, NH2. And that's one that you really should learn off at an EDTA. Then what's meant by the term bidentate? So bidentate means 2, and it's 2 coordinate bonds or 2 points of attachment. You could say either. Then state the formula of the complex formed when excess 1,2-diaminoethane, represented as En, is added to aqueous nickel 2 ions. So it's going to be 3 of those, and so nickel bracket En 3 times, and then the square brackets outside, and 2 plus for the charge. Next, trinitroamine cobalt 3, which is CONO2 3 times, NH3 3 times, is a yellow crystalline substance which may be prepared by the following method. So you dissolve 12.2 grams of cobalt ethanoate tetrahydrate in 100 cubic centimeters of hot water, cool the solution in an ice bath, and add 10.4 grams of sodium nitrite dissolved in 50 cubic centimeters of 0.88 ammonia. Cool to 10 degrees, carefully add 14 cubic centimeters of 20 volume hydrogen peroxide solution, followed by 2 grams of activated charcoal. After stirring, the mixture is left for 10 minutes before boiling for 30 minutes. Filter the hot solution to remove the activated charcoal and cool the filtrate in an ice bath. Filter off the crystals, wash with cold ethanol and dry. So first of all, deduce the formula of cobalt 2 ethane dioate tetrahydrate. So cobalt 2 means it's CO2 plus, ethanoate is going to be a negative charge, so we need 2 of those, so CH3COO twice, and then tetrahydrate dot 4 H2O. So CO CH3COO twice dot 4 H2O. And state and explain the role of hydrogen peroxide in this preparation. Well, it's quite simple. It's just to oxidize the cobalt 2 to cobalt 3. Suggest the shape of the trinitrotriamine cobalt 3 complex. So coordination number there is 6. So as we said previously, anything with coordination number of 6 is octahedral. And then deduce the coordination number, which is 6. Okay. The last bit, 20 volume hydrogen peroxide is so named because 1 cubic centimetre of the solution produces 20 cubic centimetres of gaseous oxygen on complete decomposition at 20 degrees and 1 atmosphere pressure. And here's the equation for that. So 2H2O2 gives you 2H2O and O2. So calculate the concentration of 20 volume hydrogen peroxide in mole per dm cubed. So if 1 cubic centimetre of the solution produces 20 cubic centimetres of the oxygen, it follows that 1 dm cubed hydrogen peroxide would produce 20 dm cubed of the oxygen. Now we know that at 20 degrees and 1 atmosphere pressure, 1 mole of gas will occupy 24 dm cubed. So to work out the number of moles of oxygen, we just do 20 divided by 24. So that's the volume we'll have divided by the volume of 1 mole, which gives 0.833 mole per dm cubed. And then we've got a 2-to-1 ratio here for the hydrogen peroxide to oxygen. So the concentration of the hydrogen peroxide must therefore have been double the 0.833, which is 1.67 mole per dm cubed. Number 16, propanoic acid and ethyl methanoate are isomers which can be identified using spectroscopic techniques. Explain why propanoic acid and ethyl methanoate are regarded as isomers. Nice little question that. So they have the same molecular formula but different structural formula. Then write the equation for the formation of ethyl methanoate by an esterification reaction with ethanol. So we've got your methanoic acid and ethanol, so HCOOH and C2H5OH. Remember, it's a reversible reaction. And then we've got the ester HCOO, C2H5, and then water as well. Stop doing that, iPad. So the esterification is an equilibrium reaction. Explain how you would increase the yield of the ethyl methanoate. You would either add sulfuric acid, you would add more methanoic acid, you would add ethanol, so anything on the left hand side you could add, or you could remove water because it's on the right hand side, so you can take it away. And then we've got the NMR spectrum. It says name the substance responsible for the signal at 0 and state its formula. Well, tetramethylsilane is going to be this one, and it's Si, and CH3 4 times. Then explain the NMR with reference to spin-spin splitting, peak integration, and chemical shift. So in this question, you'll be assessed on using your written communication skills, including the use of specialist scientific terms. So first thing I'm going to do is actually draw out the ethyl methanoate. So here we have, this is from the methanoic acid, and then this is from the ethanol. So you can see here there are different groups that we've got. So there are different hydrogens, different equivalent hydrogens. So we've got 3 in this methyl group, a 2 here in this group, and then a 1. So the ratio of the size is going to be 1 to 2 to 3 from those 1, 2, and 3. And then okay, so this one, I'm just going to change my pen here. So this one, which is next to the oxygen, is going to be a singlet. Then we have this one, which is a quartet because it's next to the CH3, and that CH3 then is going to be a triplet because it's next to the CH2. Then you need to be saying something about the area under the curve being proportional to the number of hydrogens in each environment. And then this one, the hydrogen next to the oxygen has the greatest de-shielding. So this is it here on the little spectrum. And the mass spectrum is shown of ethyl methanoate. So it's given you different peaks here, and then identify the ions responsible for the peaks. So you have a couple of alternatives you could have for each one of these. So at 28 you could have C2H4, so each carbon is 12 and hydrogen is 1, so you've got a total of 28 there. Or you can have just a CO, so again 12 and a 16, which will give you 28. And then 45 HCOO plus or C2H5O plus. Remember to always put your plus signs on there because it's asking for ions. And D, part 1, explain how the absorption of radiation by molecules gives rise to infrared spectra and how you would use infrared spectroscopy to distinguish between propanoic acid and ethyl methanoate. So, first thing you need to say is that the bonds in the molecules vibrate. They absorb energy of a certain frequency, and that is dependent on the atom's mass in the bond. Then you have an OH absorption peak for the propanoic acid, and you have different positions for the OH, for this one with the carbonyl group with an OH, and this one just with an O. So any 4 of those will get you 4 marks there. Then how would you distinguish between propanoic acid and ethyl methanoate using a chemical test? So really what that's asking is what's the test for an acid, which is to add sodium carbonate, and you would only have effervescence with the acid. Question 17. For a long time the bark of the willow tree, Salix alba, was used to relieve fever symptoms. The active ingredient in is salicylic acid, but it has some undesirable side effects. In 1899, the ethanoate ester of salicylic acid was found to reduce these side effects. It was given the trade name Aspirin. So Aspirin is prepared by reacting ethanoic anhydride, C4H6O3, with 2-hydroxybenzoic acid. Use molecular formula and write an equation for this reaction. So we have our C76H6O3 plus C4H6O3 gives us C9H8O4 and C2H4O2. So the C4H6O3 you can see there, and then 2-hydroxybenzoic acid is the C7H6O3. I should have said that. So what property of aspirin allows the crude aspirin formed in this reaction to be washed with chilled water as part of the purification process? The fact that it's not very soluble in water. If it was, you couldn't do that. Then describe, giving full experimental detail, the TLC method which can be used to investigate the purification process. The developing solvent is ethyl ethanoate. And this is one of the ones where you have to use your communication skills and your special scientific terms. So, points on the mark scheme where have a TLC plate with a pencil line and mark 3 spots on it where you're going to put your dots. Then dissolve small amounts of the crude, purified and the pure aspirin in separate test tubes in a suitable solvent like ethanol. Spot each sample onto the TLC plate, then place in a developing tank with a suitable solvent like ethyl ethanoate. Then remove the plate and mark the solvent front, and then use UV light or a locating agent to find the spots. And the way that was marked, 5 points would have 5 of those points would have given you 6 marks, 4 would have given you 4, and 3 would have given you 2. And finally, suggest why TLC is preferable to GLC for this preparation. You could have said either something to do with the cost or to do with the volatility. So that is the end of the specimen paper for Unit 5.